So today in this video we're going to talk about exponential sequences and exponential functions, and specifically how to construct exponential functions, how to graph exponential functions, and how to analyze those graphs afterward. So let's get going. It's not much different than what we were doing with geometric sequences, so let's get going. So first of all, this is the general equation for exponential functions. It would be y equals a times b raised to the x power. Okay, and I hope this looks a little familiar to you because if you remember from geometric sequences, when we were writing a rule, an equation for the rule of our geometric sequence, you would say it was f of n equals f of 0, right? F of 0, that means x equals 0, so that right there should jump out at you as being your y-intercept, which in our exponential function equation, that a does stand for the y-intercept. So it was f of 0 times your common ratio. Now, what was your common ratio? Your common ratio is what you were multiplying by, which is no different than this b here in our exponential function equation. That's just what we're multiplying by, raised to the x power. So these are virtually the same. Same thing you were working with today and the day before today. So let's go ahead and talk about this b a bit more, though, and analyze some behaviors associated with b, which is the multiplier. That's what we're multiplying every time. So first, if b is greater than 1, we say that we have an exponential growth. Now, our exponential growth could be either negative or positive, and we'll probably talk a bit more about negative exponential growth tomorrow in class. But this right here would be your exponential growth. And as you can see, your multiplier is 2. It would be greater than 1. And as your domain increases, right? And domain, remember, is x. So as you go towards positive infinity on your x-axis, as your domain increases, what happens to your range? Your range is also going to be increasing. Your range is going to go towards positive infinity as well. So with exponential growth, we're increasing, right? We're increasing. Now, what's happening at the back end of this exponential function? Well, it looks like we are getting closer and closer to this y equals 0 line right here, okay? But we're not touching it. And we spoke about this a bit today. There's a special word for it. We're going to talk about it in a moment. But first, let's get to this. This is decay. So what does it mean when we have a decay? Well, if b is less than 1, so if b is a fraction, we say that we have a decay. And with a decay, as your domain, as your x values increase, what do you notice about this exponential function? As the x increases, as the domain increases, the range, it gets smaller and smaller and smaller and smaller and smaller. But remember about what we spoke about today. Is it actually, with this function, are we actually ever going to touch 0? Are we ever going to cross 0? No, it's just going to get smaller and smaller and smaller and smaller, but we're never going to actually cross the y equals 0 line. We're never going to cross it, and we have a special name for that we talked about today. We called that an asymptote. So an asymptote is a line which the graph gets close to but never touches. And here's an example of asymptote, but I feel like it'd be better just for you to see an actual problem that we work out where you could actually see the asymptote and work it out on your own. So we are just going to move on to our first example. Let's take a look at this first example. So remember, the equation that we use for exponential functions is y equals a times bx, where a is going to be your starting point. You could consider it your y-intercept, but that might change depending on whether we add or subtract anything on this end. And if you remember from previous lessons, that'll shift the whole graph up or down, and we're going to do an example of that in a moment. But for now, let's just consider a to be our y-intercept or our starting point. And remember, b is going to be your multiplier. So let's take a look at this problem. It's y equals 3 times 2x. So we're not adding or subtracting anything, so our graph isn't going to shift. It's not going to shift up or down. Okay, so that means our y-intercept is in fact going to be 3. Our starting point is going to be 3. So how would you graph this? We're just going to create a table. Okay, and we're saying that our y-intercept is 3, so I'm going to go ahead and put that as our starting point, 0, 3. And it makes sense, because if you plug in 0 for x, 2 to the 0 power would be 1, and 3 times 1 is 3. Okay, and now let's go ahead and just get some more points that we could put on our graph. So let's go ahead and do 1 and 2, and let's go ahead and do -1, and let's go -2 as well. So remember, our multiplier is 2. That means we are multiplying 2 each time. So as we go forward, we are going to be multiplying 2. So our first term would be 3 times 2, which is 6. And if we go forward again, our second term would be 6 times 2, which is 12. Okay? Now, if we go backwards, instead of multiplying by 2, we'd be dividing by 2. So at -1, we would be at 1 1/2. And if we divide by 2 one more time, we would be at 3/4. Okay, now let's go ahead and graph this. We probably won't be able to include this point on here, but let's graph the other points. So at 0, our y-intercept is going to be 3, so that would be right here. Okay, at 1, we have 6. Okay, at -1, we have 1 1/2, which would be right here. At -2, we have 3/4, which would be somewhere around here. And if we go ahead and graph this, so this would be continuous. They didn't give us a set domain. This would be continuous, so we'll go ahead and connect this with the line. Now, if you notice, our b originally was 2, right? Our b was 2. Now, 2 is obviously greater than 1, and I always told you, I'm sorry. I told you at the start of this lesson that when your b is greater than 1, it means that you are going to have a growth, and you can see that because on your graph here, as you approach positive infinity on your x-axis, as your domain goes towards positive infinity, what happens to your range? It also goes towards positive infinity. So this is going to be a growth, because as we go towards positive infinity, our range goes towards positive infinity. What happens as we go towards negative infinity on our domain? Well, it looks like we get closer and closer and closer to this line right here, which this line right here is y equals 0. Let me do it in a different color. Let me do it in blue. Get closer to y equals 0, but we never touch it. Okay? So our fractions are going to get smaller and smaller and smaller and smaller, as you can see over here. They're going to get smaller, but they're never actually going to become 0. They're never going to become negative. We call that an asymptote. So in this case, what would our asymptote be? It would be y equals 0. Okay? Because that is a line that we are going to be approaching, but we're never going to touch. We're going to get close to it, but we're never going to cross it. Okay? What would the range be? Well, it looks like our range is going to be, remember, range was y. And what is this graph doing? As if you could take a look at it, it's going towards positive infinity. So our range is going to be y is, our asymptote is 0, right? So we're going to have 0 here. And what's happening at 0? We're going towards positive infinity or negative infinity? Looks like we're going towards positive infinity, so that means y is going to be greater than 0. To be greater than or equal to? No, because remember, y is never actually going to be 0. 0 is our asymptote, which would mean that we are never actually going to cross 0. What would our y-intercept be? We know that already. Our y-intercept is going to be 0, 3. And what would our domain be? Our domain is going to be all reals. If you scan this from left to right, it's going to be every single x value. It will be all real numbers. All right, so I want you to just do this one on the same graph. Just try to get a different colored pen if you have a different colored pen, or maybe a colored pencil. And the reason why I want you to do this in the same graph is because I want you to notice what's going to happen now that our A is negative. So pause this video and try to think of what you think is going to happen now that our A is negative. So remember, the formula, the equation for an exponential function is y equals a times b raised to the x power, where a is going to be your starting point or your y-intercept unless we shift up or down. So in this case, our y-intercept is going to be -3. That's going to be our starting point. And our b, our multiplier, is going to be 2, which means we're multiplying by 2. So if we create a table, so our starting point, we'll put -3 here on the y, and we know that means that's going to be our y-intercept, so that means that x is going to be 0, right? And if you put 2 raised to the 0 power, that's 1, and 1 times -3 would in fact be -3. So -1, -2, 1, and 2. So our multiplier is 2, which means we're multiplying by 2 every time, right? So -3 times 2 would be -6. And then -6 times 2 would be -12, which we wouldn't be able to fit on our graph, just like our last example. And if we go backwards, we divide by 2. Okay, so -3 divided by 2 would be -1 1/2, and if we divide by 2 again, that would be -3/4. So let's take a look at what this does to our graph. So again, our y-intercept is going to be 0, -3, which is let's do this in black, right here. So then at 1, we were at -6, which is going to be right here. At -1, we are at 1 1/2, which is going to be right here. And at -2, we are at 3/4, which would be right here. Okay? So this would be our exponential function. So what did this do? It just reflected it along the x-axis. Okay? It reflected it along the x-axis. So let's go ahead and first discuss whether this is growth or decay. This is going to be a growth, and I'll explain why this is going to be a growth a little bit more tomorrow, because this video has already been a little bit too long. But this would be a growth, would be what we call a negative growth. And what would our domain be? Our domain would still be all reals. What would our range be? Well, first let's talk about our asymptote. Remember, asymptote is the line where our exponential function approaches but never crosses. And once again, that looks like it's that y equals 0 line. Okay, and it looks like we're getting closer and closer to y equals 0 as we approach negative infinity, but we're never actually going to cross it. So our asymptote is going to be y equals 0. What would our range be? Okay, so our asymptote is 0, right? Now what's happening at 0? It looks like we are going down. We're going towards negative infinity, so that means y is going to be less than 0. Okay, not less than or equal to, because remember, we're never actually going to include 0. We're never actually going to touch 0 or cross 0. Okay, and our y-intercept would be 0, -3. Just one more I want to do with you. So this one, again, remember our exponential equation is y equals a times b raised to the x power, where a is your starting point, but starting point. But take a look at this problem here, or this exponential function, because this time we have a -4. So what do you think that is going to do to this entire function? So pause the video and think about that for a moment. Well, let's just see what it does. Let's go ahead and set x equal to 0, which would mean that would be your y-intercept. And what happens when x equals 0? Well, 2 to the 0 power would be 1. Anything to the 0 power is 1. 3 times 1 is 3. 3 minus 4 is -1. So what happened? Our y-intercept went from 3 to -1. It shifted down 4 spaces. So what this does is it's either going to shift down, or is either going to shift your exponential function down, or it's going to shift it up, depending on whether we're subtracting or adding. That's all that does. So this is actually going to shift our entire function our first function down 4 spaces, okay? So originally, our y-intercept was 0, 3. Now we're shifting down, so it would be 0, negative 1. Okay, originally at 1, right, it was 6. But now we're shifting down. So at 1, it's going to be 2 because we're shifting down 4. Okay, originally at 2, it was 12, but now we're shifting down. So at 2, it's actually going to be 8 because we're shifting down 4. Okay, and then originally at negative 1, right? At negative 1, we were at 1 and 1/2. So if we subtract 4, now we'd be at 2 and 1/2. Okay? And originally at negative 2, we were at 3/4. But if we subtract by 4, we would be at 3 and 1/4. I'm sorry, these should both be negative. We'd be at negative 2 and 1/2 and negative 3 and 1/4. So let's go ahead and graph this. So our y-intercept is going to be 0, negative 1. Okay, so that would be right here, 0, negative 1. This isn't working. Okay, and then at 1 we're at 2. At 2, we're at 8. Okay. At negative 1, we are at negative 2.5. Right here. And at negative 2, we are at negative 3 and 1/4. Okay. So if you look at this, didn't mean to switch colors, but whatever, I'll keep it. Looks similar to our first graph, except we shifted down 4 spaces, okay? So our domain would still be all reals. Let's talk about the asymptote now. The asymptote would not be y equals 0 because this time it looks like the function is going to be approaching this line right here, which is y equals negative 4. Okay, it's never going to touch negative 4, but it's approaching negative 4. So your asymptote is going to be negative 4. Which means your range, well, what's happening at negative 4? We're going up, so it means your range is going to be y is greater than negative 4, okay? And this would obviously be a growth. Again, and the reason why it would be a growth is because b, again, is greater than 1. We're going to do some more examples of these tomorrow, okay? Have a great day. See you tomorrow.